All right, I will begin with a word of prayer. I think it's time. So, here we go. Dear Father, we thank you for this day. I thank you again for these students and for the pleasant weather outside and just for your many blessings to us. Just pray that you be glorified through what we do this day, that we could all just understand what we need to about this math. And again, Lord, we just thank you for your many blessings. In your name we pray, Lord Jesus. Amen. Here's the top hat. So I think what I'll start with is just some things on the board. All right. So let's just look at one of these here. Diagrams with 3 sets. All right. So suppose this is A. Suppose this is B here. And suppose this is C. All right. Then I want to ask you if you could tell me, in terms of set operations. Sorry, guys. I won't be on that board the whole time. This will pass. Can you guys see? I don't know. Yep. Oh, okay. Oh, good. So, all right, we'll start out. So what if I start here? What's this region that I've just shaded in here? Let me call this 1. Yep. So I say 1 is A intersect B intersect C. Very good. That is what that is. Let's see here. What if we threw in, let's see if we can describe this one here. We call this 2. What's this region? Yep.
Intersection of A and B.
So you say 2 is the intersection A intersect B. I think that's not, you're not wrong, that's part of A intersect B, right? But if it's just the red part, what do we have to exclude? C, right? So how can we exclude C? How can we say it's not in C? To say it's not in C, right, is to say that it's in the complement, yeah? In the complement of C, right? So if we just take this and we intersect it with what we called C prime, right? The complement of C, then that will just be the red region. See, because that means that a point in A intersect B intersect the complement of C, that means that it's in both A and B, but it's not in C. So that would be that region. All right. Now, the gentleman who spoke up, you're exactly right. If we take the union of regions 1 and 2, what do we get? 1 union 2. Like both of those together, that would exactly be A intersect B. Right? So the union, this whole piece right here, that would indeed be A, did I say A union B? I mean A intersect B. A intersect B, right? All right. How about this? How would you describe region 3 right here? All right. What would that be?
B intersects C.
I heard B intersect C, right? Okay, so that would give me all of this, right? So you got to get rid of the part that's in A, right? So to get rid of the part that's in A, we need that it's also not in A, right? Which is to say intersect with the complement of A, right? All right? So far, so good? All right. Do one more of these over here. Sorry, guys. All right, so here I'm going to ask the question a little bit different. If I had A union B, and I take the complement of that, the complement of A union B, where should I shade in? How can I picture the complement of A union B? C. That's too much. See, because part of C is also in A union. Let me draw A union B. What does A union B look like in this picture? It is, well, let me pick a marker you can see, possibly. That's a bad choice. I should, bad choice. Where's my eraser? Here it is. Yeah, a t-shirt will beat these all day long. Never use these. They just make a mess. Oh, see, these whiteboards hardly ever get used because everybody here just blathers on off a PowerPoint, right? But so the A union B is this, but it's also this, right? It's everything in A. It's everything in B, right? All of this is in A union B. The complement of A union B is everything that I haven't shaded in yet. Yeah, so the complement of A union B is just this piece down here. If you're colorblind in such a way that you can't see the difference between red and purple, my apologies. I only have so many markers. So this is in red, right? Up here in the purple, A union B, right? So I thought I should take a few minutes of class just to show you some more pictures of these because there's a little bit of that missing in my PowerPoints, okay? You could also cheat and read the book if you wanted, right? So, I'm joking, it's not cheating. Oh, you moved the, thanks. No, you're fine, let me, I have a suspicion I need to, well, yeah, it's silly. Podium's in the way. I hope you've top-hatted because I'm about to put it away. All right. There we go. What's that?
You can tell me when to move.
Oh, I know. It's the tricky. The zoom part is the annoying part. Yeah. But thank you though. There we go. It's working. Okay. Yeah. All right. So here we are. Any questions before I go on? All right. So as I was mentioning, I'll be gone after this class. You can send me an email. I'll get back to it eventually. All right. I hope you noticed that you can still work on the homework. The first homework, I extended it to this Thursday because I had a few people who were, in trouble. Now, if you didn't notice yet, I'm sorry, but it's there. All you got to do is go to the Module 1, click on the thing again. It should take you to it if you missed something. I think most of you are done with it, so. Let's see here. As we talked about last time. Come on. As we talked about last time, the intersection, when we read about a word problem that involves and, we think intersection, right? And we think about a word problem that involves or, it's probably a union, right? Now, there we go. Let's go on here. So we talked about the inclusion-exclusion principle, remember? For 2 sets, it's pretty easy, right? But we started working on last class this example, right? We had an Italian restaurant. It had 495 people surveyed, 320 liked pizza, 395 liked stromboli, 295 liked spaghetti, and then we had 280 who liked both pizza and stromboli, 190 liked both pizza and spaghetti, 245 liked stromboli and spaghetti, and 160 liked all 3. And I started explaining to you how we can figure out like the number of people who like, say, just pizza and stromboli, but not, well here, like how many people just like spaghetti is something we can answer if we just sort of sort through the Venn diagram. So I fixed the mistake that was in the PowerPoint that we discovered last time, right? So if I want to calculate the number in A intersect B, what I can do is I can calculate the number in A intersect B intersect C plus the number in X, right? Now the number in X, that would have been what? That would have been like the number in A intersect B intersect what? The complement of C, right? But anyway, so the number in X here, it's got to be X plus 160 is equal to the number in A intersect B, right? Because we were given the number in A intersect B is 280, so I find 120, right? What would that mean in the context of here? What does X represent? People who do what? They like pizza, they like stromboli, right? But the people who fall under category X in the survey, these are the people who don't care for spaghetti for whatever reason. Yep.
Why would 160 be the complement of C if the complement means it's not C and...
Oh, that's not the, what I was saying is X is the, what X is, I didn't ever say what X is here, but if I was to say what X is, it's the number in A intersect B intersect the complement of C. I didn't write it on the PowerPoint, but I wrote it over there.
Yeah, but why would 160 be included in the complement of C? Because doesn't the complement mean like not C?
Oh no, 160 is not included in the complement. 160 is the number in the intersection of A, B, and C. So I've got like 160 here,
Right.
apparently 120 in X.
Okay.
I may be hearing you, but not hearing you. I'm not sure. It's okay. Anybody have a question similar to hers they want to ask? Or different? It's also fine. Sometimes students ask a question and I don't hear it, but then other students hear it and they can reformulate it for me in such a way that I can answer it, sometimes. There's 100 of you here in principle, so odds are high. This is the one thing I like about large lecture sections for math. There's a downside. I don't get to know you as well, but the upside is I tend to have a larger collection of good questions in a large lecture section in my experience, right? It's more likely that there's a couple of you in here who have interesting questions than if I had 10 students, Okay, so then what? So we could figure out what Y and Z is, right? Let's see here. Let's figure out how many are in. So what would Y symbolize? Y would be what? People who they like what? They like pizza they like spaghetti, but they don't care for this stromboli. So how would we figure out what y is? What would the equation we need to look at be? Yep.
Y plus 160 equals 190.
Y plus 160 equals to 190. Do you guys agree with that? See, because A and C is 190. So there has to be 190 in this and that, right? So 160 plus whatever y is should be 190. What does that make y? It makes y 30. 30. So y would be 30. Let's see here. Y would be 30. How about z? Can we figure out what z would be? How would we figure out z would be? Z would be the people who what? It would be the people who like spaghetti and stromboli, but don't like pizza. These are really weird people. Who doesn't like pizza? Let's see here. Communists probably. Let's see here. 160 and are communists good or bad? They're bad? Are you sure? Okay, it's good. I wonder if we drilled down into that, if you really believe it. Let's see here. 160 and z. So what would z be? 160 plus z should be equal to? 245. So what's 245 minus 160? It is 85? 85? $160? Wait a minute. I need to write this down. Sorry, guys. So we'd have I was trying to figure out z, right? So I should probably not write this. 160. It's kind of permanent. 160 plus z equals to 160 plus z equals to 245. So that makes z equal to 245 minus 160, which you guys told me is 185? 85. Oh, 85. Thank you. So z is 85. All right. If some of you couldn't see that, I'm sorry. This room is hard to work with sometimes. I taught physics in here before. That was worse. Because physics you can't do in a PowerPoint. Like you got to write stuff out in physics. And I only had 70 in here, but it was abysmal. I actually put up another board up there temporarily. It was about 10 degrees off. It was crooked. I had a lot of course evaluations complaining about the crookedness of the board. I felt like I'd done my job. So if I can distract them with the crookedness of a board as opposed to the poor quality of the teaching, I feel like I've done a good job, you know? But I'm just kidding. The board wasn't that crooked. Okay, so here's the story in general. This is not in your book. For reasons I still don't fully understand, I was once asked to give a guest lecture in combinatorics in an interview I had at a university. And so I gave a talk on this thing called the Exclusion Principle. And this is a slide from that. So the Exclusion Principle, so this notation I'm using here is not the notation in your book. Some people just use bars instead of n. I've been using n for the number of things, right? So like the number in A union B, it's the number in A, the number in B, minus the number in the intersection. The formula, if you want, I don't recommend it, the formula for three things is the number in A union B union C. It's the number in A plus the number in B plus the number in C minus the numbers in the intersections, all right? And then plus the numbers in the triple intersection. So you have to remove these because of the double counting, but at that point, the middle one you removed one time too many, so you have to add it back in. And this continues plus minus plus minus plus minus if you had union of more sets. This is the general inclusion and exclusion principle. If you don't understand this, it's really okay. I just wanted to show you there is a generalization for n sets. And also, I don't think this formula is especially helpful. So that's why we didn't work the last example with this formula. We could have worked the pizza, spaghetti, stromboli problem with this formula, but I think the picture is way easier to think through. All right? So anyway, enough about that. Any questions? Okay. Oh, by the way, I didn't get the job for that interview. I think I made it. I think I told them too much. They wanted a less extravagant lecture. That's usually the mistake I make in interviews. If you're ever trying to get a teaching job, always teach easier than you think it should be, as a general rule. Okay, so here it is. This is another thing we haven't talked about yet. A and B be sets. We define the set difference. Okay, set difference, which we could do A minus B. What would A minus B be? This is the set of points, all right, which are in A, but they're not in B. All right. In contrast, B minus A, these are the set of points which are in B, but they're not in A. All right. And here's a picture of it. So if we have A and B, A minus B is the blue part. B minus A is the red part. What's green? I didn't label it, but you can tell me what it is. Not B, no, not B plus A. I haven't defined B plus A. I know you're like, well, you did minus. There's got to be a plus. No, there's no plus. I know. It's what? Yeah, B intersect A, right? That's the intersection. So does this make sense? If we look at the union of A and B, there's three cases, right? A minus B, the difference of A by B, the intersection, the green part, right? Or the red part, which is the part of B which is not in A. And these are mutually, these are distinct categories, right? So you could count, you could do a counting problem here. If you knew the number in A minus B and you knew the number in B minus A, that would allow you to figure out the number in the intersection if you also know the total number, you know? All right, silly exercise. I have 1, 2, 3, 4, 5. And then I have 3, 4, 5 gummy bear and sleeping tiger. All right, and I've asked us to find the slept differences? No, set differences. Slept's not even a word. That's wrong with me. I decided to abbreviate gummy bear as GB and sleeping tiger as ST down here. So A minus B, what do we have? We have X in 1, 2, 3, 4, 5, such that X is not in 3, 4, 5 gummy bear sleeping tiger. So what X is that? So over here, 3, 4, 5, we have to exclude, right? So we cross those out. What are we left with? 1 and 2. Any questions? And what is this like? What did we talk about already that this is sort of like, but it's different? Remember we talked about the complement, like A prime? Well, that was also a set difference, but what was the difference? We're taking the difference of the set from the universal set, right? So there we had like the universe of all possible elements in our context. In contrast here, we're taking the difference of A by B. So A could be smaller than the universe. We're just getting rid of some of A. Yeah? But it's essentially the same idea. Now, B minus A, so we're looking at X that's in B, that's not in A. So in A we have 1, 2, 3, 4, 5. In B we have 3, 4, 5 gummy bear, sleeping tiger. So 3 and 4 and 5 we have to get rid of because they're ones we're excluding because they're in A in this context. And that just leaves us with gummy bear and sleeping tiger. So, is good? Okay. I can go on? Okay. So So I'm really going on. So the next topic we have in here is infinity. Now I've talked a little bit about cardinality before. In like the first lecture I think I did. Talked a little bit about, maybe the second lecture, I can't remember. But remember we talked about whether the natural numbers and the integers and the rational numbers were the same size, right? So this is continuing that discussion, yeah? And so a set is countable if and only if it's either a finite set or it's an infinite set that's equivalent to the set of natural numbers, all right? All right, so every infinite set that is countable has what's called cardinality aleph naught. This is a Hebrew, part of the Hebrew alphabet, right? Aleph. How many of you guys taken Hebrew? Oh man, nobody? Well, I haven't taken it either, but I do know this is a Hebrew letter. Let's see here. So an infinite set that is not countable is said to be uncountable. Because the set, now this is just a very, if you've had other math classes, what's our usual notation for A? I'm going to put a board up, like, oh, sorry if I shine the laser in your eye. I'm going to put a board up here so I can write here. Wouldn't that be nice? As long as it's not crooked. Yeah, I'll put one over there too. So I'm going to do. I'm going to do it. It wouldn't be prudent, but I still am going to do it. Let's see here. So that set A, in the usual notation on the number line, you've got 0, you've got 1, X is in here, right? So our usual notation for A is just the open interval from 0 to 1. If you've had other math classes and you remember them, it's the interval from 0 to 1. That's A. Okay? That's this A. So what that is just a little bit of the number line, right? So what this is saying is that that little bit of the number line is bigger than the natural numbers. It has a larger size. There's more numbers between 0 and 1 than there are in the entirety of all of the counting numbers, or all the fractions from what we talked about before. All right. And then Cantor used the letter C, which is the first letter of the word continuum, to represent the cardinality of A. So the number, the size of the interval from 0 to 1 is called the continuum. All right? So here's some trivia for you. The natural numbers, the cardinality is aleph naught. The integers, the cardinality is aleph naught. The rational numbers, the cardinality is aleph naught. All right? But irrational numbers, all of the real numbers which are not rational, like pi, for example, 3.14159, yada, yada, yada. Yeah, that's an irrational number. The square root of 2, irrational. Tons and tons of irrational numbers, actually. As many of those as there are real numbers, actually. Basically, if you take any subset of the number line has the size of the continuum. And then the real numbers itself has the size of the continuum. Now, what this means is it just a fancy way, well, it's a shorthand for reminding mathematical people that there exists one-to-one correspondences between these different things here. So these all have the same cardinality C. That means that there is a bijective correspondence between this and that, or that and that. You can make a one-to-one mapping from one to the other. All right? That's what that means. What Cantor showed was that no matter how large the cardinal number of a set, we can find a set that has a larger cardinal number. So you take whatever number system you have. He gave an argument which showed that you could find a bigger number system with a yet larger form of infinity. All right. See, both aleph naught and C, these are both forms of infinity. All right. And anyway, Cantor's theorem, let S be any set, the set of all subsets of S has a cardinal number that is larger than the cardinal number of S. All right. So I discussed that some in lecture 2 for a finite set. I mentioned to you that the number of sets in the power set of a set is 2 to the n, right? We looked at the example where we had a set with 3 elements, right? And then we looked at a set of subsets. There were 8 subsets because 2 to the third was 8. We worked the pizza problem. We talked about if we had 10 toppings to the pizza, that would mean that you could take a collection of those toppings to put on the pizza, right? And if you have 10 toppings, how many subsets are there? There are 2 to the 10th. There are 1,024 possible subsets of those 1,024 possible topping choices if you have 10 toppings, all right? You had one in your homework about a sandwich, right? Same idea. But when the set is infinite, we can't say the actual number, but we can say is its size is aleph naught, or it's the continuum, or it's something beyond that. Infinity's weird in terms of its arithmetic. So transfinite means beyond finite, all right? It's not like numbers identifying as finite or something. But here we have, it's weird. I mean, you can take infinity and add a number to it. You still get infinity back. Right? Aleph naught plus a number, it's still aleph naught again. You subtract a number, you still got aleph naught. If you add aleph naught to itself any finite number of times, you still get aleph naught, or aleph null as it says here. Some people call it aleph null, fine. That's weird, right? If you add 5 to itself 7 times, what do you get? 5 plus 5 plus 5 plus 5, I lost track. But 5 times 7 is what? It's 35, right? When you take finite numbers and you add them to themselves, you don't get the same number back again. So the way infinity behaves in terms of its arithmetic, it's really weird. Yeah? And the same is true for the continuum. Like the next infinity up still works the same way. Also, if you add something, if you add the continuum to aleph naught, you just get back the continuum. Basically, continuum doesn't even see aleph naught. It's so much bigger. And if you multiply the continuum by aleph naught, you still get the continuum. All right. So these are things that can be defined in something called transfinite arithmetic. So this is just really a point of trivia for you guys. I don't think I've asked you any homework problems that are about this, if I remember right. So with that, are there any questions about homework? Nothing? Everybody top-hatted? Let's see here. Well, I think that's it for today then. I'll let you guys go early, if that's okay. Oh, okay. Okay.